So let us design an algorithm for sequence consensus that is based on the single value Paxos. Our goal here is to have a correct algorithm, but not necessarily efficient one. We will start by reviewing Paxos in more detail and then modify the algorithm to get a new algorithm that agrees on sequences of values. So here is the roadmap from Paxos to Sequence Paxos. We will make the minimal modification to Paxos to obtain a correct Sequence Paxos algorithm. Then we add optimizations to make the algorithm efficient while preserving correctness. So let us remember single value Paxos. In this algorithm, any process can propose. And in Paxos, a process may assume any or all of the three roles: proposer, to propose a value, acceptors, that accept values, and learner, that learn the decided value. So here is the initial state of Paxos algorithm. For proposer, we have a proposer round number or ballot. Initially it is 0. And we have a proposer current proposed value. Initially it is undefined. The acceptor has n promise, which is the promise not to accept any value in a lower rounds. We have the current round number in which a value is accepted, and we have the accepted value, of course, which initially undefined. And the learner has one value, v, which is the decided value. So here is the single value Paxos algorithm, which, just to remind you. So the first thing is a proposer. When he gets a proposal request from a client, it creates a unique higher proposal number, higher than whatever is known at this point. And it uses two variables. The set S will be used to gather accepted values, and the X, which is, will remember the number of acknowledgement in what we call the accept phase. You are going to see that. So what it does, it sends a prepare to all acceptors. And if this number in the prepare phase is higher than what is promised before by the acceptor, then the acceptor updates its promised number and then sends to the proposer the current value accepted and its current round number, and just to say, okay, I'm responding to this prepare message. When a proposer gets a promise, it adds it to the set of promises here. It adds the pair, the round number, and the value v. And whenever it gets a majority of promises, then it looks to the set S and selects an element, kv, such that k is the highest proposal number, okay, or highest round number. And then if that value is not undefined, then it sets its proposal to be the value selected in this max set. Otherwise, if the acceptors say we don't have any value, then it sets its value to propose it, the original value C. And then it sends to the acceptors, please accept at my proposer number P the value V. That's what it does. So when an acceptor gets a value V with the proposal number n. If that is equal to the promise or higher than the promise, it's again sets its promise number, and then it updates its accepted value. That is, I think it's clear. And then it sent that n is accepted. This is the round numbers accepted to the proposer. When a proposal gets a majority of acknowledgement, in this case, then it can decide on the value it has proposed. Okay. And if it decides on that value, it sends it to all learners. And that's what happened here. And the learner triggers just a decide. In all other cases, a negative acknowledgement is sent, and on a negative acknowledgement you abort. This is abortable Paxos algorithm. Now let us move from this algorithm, which we know, and I'll just want to remind you with a few things about this algorithm. First, that we can call this part of the algorithm, until actually this point, is the prepare phase. And once it sends an accept message to all acceptors, this part, it is called the accept phase. So it's a two-phase algorithm. So now let us move from Paxos to Sequence Paxos. Values are sequence, and initially, instead of using undefined, everybody accepts an empty sequence. So this is the empty sequence. And we make two changes. One is that after adopting a value with the highest proposal number, you remember this is the one that we adopt by selecting from the set of pairs the one with the highest proposal number, the proposer is allowed to extend the sequence with new commands. We allow here to extend the sequence with new commands. It could be a duplicate command, or it could be a non-duplicate command. We will address this issue just very soon. And the learner that receives a decide will decide if V is a longer sequence than any previously decided sequence. So here, let's discuss the issue of agreeing on commands and if we allow duplicates or not. In fact, a client is allowed to issue the same instance of a command multiple times. The reason is very simple, is that a client will talk to one of the proposers, please propose this value, but the proposer could crash, and then the client, after timeout, will issue the same command again. That's clear, huh? And so we cannot really avoid proposing the same command multiple times. At this point, we are going to hide this issue in the sequence Paxos algorithm in the so-called sequence append operator. So we can have two versions of the same algorithm that's going to be described. One that does not allow duplicate commands. So this is an append operator, so I'm asking to extend a sequence with one more commands. And if the command is already in the sequence, we just return the same sequence. Otherwise, we extend the sequence with a new command. This is a so-called non-duplicate append operator. If we define an append operator that allows duplicates, then it has a very simple definition, which is basically, if I want to append a command, I just add it in the end of the sequence, at the tail of the sequence. Here is the initial state of sequence Paxos. The proposal number is the same, but now the initial proposed sequence is the empty sequence. The promise is the same. The proposal number of what is accepted by an acceptor is the same, but all acceptors accept initially the empty sequence. And for learners, a learner also accepts the empty sequence. So here is the sequence Paxos algorithm. The proposed phase from a proposer is the same as before, by sending a prepare to all acceptors, and when an acceptor gets prepared with n higher than its current promise, it sends a promise to the proposer with its current accepted value and its round number that has been accepted in. Then we come to the promise. The proposer collects a majority of promises, and in that case, if it gets a majority of promises, that's the case here, then it looks to the set of all pairs, a pair of a round number and the sequence, and selects the sequence with the highest round number as before, but now V is a sequence. And then what it does, which very changing now compared to the single value Paxos, it just appends the command to that sequence here. It appends the command to that sequence. And we know we have two variants of how to append a command. And then it basically sends this new sequence to all acceptors, which is fine. The sequence could be accepted if the proposal number is still the highest one. There is no other proposal promised by any acceptors. And in this case, if you collect a majority of the so-called accepted messages, this is like acknowledgement message. If you collect a majority of these, then you know that there's a majority of acceptors that accepted this sequence, and you can decide. On deciding by sending that sequence to the learners, and if that sequence is less than what already decided, then you trigger a new decide with a longer sequence. In all other cases, the algorithm basically aborts. And as you can see here, it can abort here, it can abort here, and here is the case where the proposer aborts. So let us just stress one point here. And the real change we did was only here in this algorithm. We adopted the sequence with the maximum proposal number, and now we are doing maximum on comparing a number and a sequence, and we appended our command, our proposed command to that sequence. And here is the definition of max. You have a set, and this set has a pair, which is the number and the sequence, round number or proposal number and a sequence, and it basically selects the one with the highest proposal number and return it here. That is the one. In the algorithm, as we described, these numbers will be distinct, but later you will see that it will not be distinct. And in this case, if the proposal numbers are equal, we select the one with the longest sequence. So as you can see, we had a minor modification here. We just changed one line in the code, more or less. And in fact, this algorithm, very similar to Paxos, and it is correct algorithm. We have two aspects here to consider. One is the correctness, and one is the efficiency. So in the correctness, it's easy to show, and we're going to show in the next unit, that if we just follow the steps of Lamport when he defined the correctness proof of a single value Paxos, then the correctness proof of Sequence Paxos would be just modeled after that single value Paxos correctness proof. And it's very simple. It's extremely simple. And you will see that all properties that we just defined for Sequence Paxos will be satisfied. So that is fine. But this algorithm has a huge efficiency problems. So every proposal takes 2 round trips. As you can see, when a proposer gets a value to propose or a command to propose, then it goes to a prepare phase, which is 2 communications steps, and goes through an accept phase, as we said. The other aspect is that proposals are not pipelined. In this algorithm, there's only one proposer at a time, and it has to go through the accept phase and be decided before new proposals could be actually decided. The third aspect is that if you think of the algorithms, we are actually sending back and forth sequences. That is a problem. And we are decide carries sequences, and this could be arbitrarily long. So what do we want to do? What we want to do is that we would like to skip the contention on having multiple proposals contending at the same time to propose. For a command proposed to be decided, the proposer has to be alone in the system during the prepare phase and the accept phase. For this, we are going to use what we call a leader. And a leader will be the one that should propose commands. So that is one thing. The second thing, we would like that the proposer, which is a leader, to be able to skip the prepare phase. So in that sense, we would like any command will be accepted in one round trip. Then we would like proposers to be pipelined. So you can propose multiple proposers, and this will be pipelined one after the other without the first one or the previous one being decided. And we would like now not to send sequences back and forth. We just would like to send new commands and deltas of sequences, the one that was not sent, were not sent before. And we would like, of course, the decide to produce an incremental stream of new ordered commands. So again, just to stress, you see, a proposer has to go through the prepare phase and the decide phase before deciding. 2 round trips. The commands here are sequences. They are sent, as you can see here, and then sent back here. These are sequences that are going in the system back and forth. And here, and also sent there, as you can see. So the algorithm as defined is correct, but not efficient. So the next unit will address the issue of correctness, but if you believe the algorithm is correct, you can go further to how to move from this correct algorithm to a very efficient Sequence Paxos algorithm.